Space is big, light is fast. Unfortunately, not fast enough. Star Trek promised us warp drive 60 years ago. The universe says no. But why not? These are 10 challenges to building a warp drive, and this is number 1. What is the speed of light? Light circles Earth 7 times in 1 second. That's 299,792,458 meters per second. Fast enough to get from London to Sydney in 1/10 of a second. But it's not fast enough to explore the galaxy. Now, Alpha Centauri, our nearest star, our nearest neighboring star, it's like 4.37 light years away. Even traveling at light speed, you'd spend over 4 years getting there. And you can't reach light speed anyway. You see, Einstein showed that mass and energy are equivalent through E equals mc squared. When you accelerate something, you're adding kinetic energy, and that energy contributes to the object's total energy, which is what resists further acceleration. As your speed gets closer to light speed, that resistance, it's what we call inertia like inertia, you get it, that increases dramatically. Each push adds less and less speed because more and more of your energy goes into that growing inertia rather than motion. We used to say that the particle gets heavier or the person gets heavier, we add mass, and we used to call it relativistic mass, but it's not quite right because you don't actually gain mass, it just takes more energy to keep speeding up. Now, a proton at 99% of light speed has about 7 times the total energy of a proton at rest. At 99.9%, it's 22 times. At 99.99, it's about 70 times. Every extra 9 that we add to a speed multiplies the energy that you need. At exactly light speed, the required energy would shoot to infinity, and the universe doesn't contain infinite energy. Not in all the stars in every galaxy in the universe, or the observable universe, or the non-observable universe. This isn't an engineering problem where better rockets would help. It's mathematics. The equation approaches infinity as you approach light speed, and physics doesn't do infinity. So we're stuck. The galaxy is vast, light speed is impossibly fast but still too slow, and we can't reach it anyway. Unless there's a loophole. But that's for the next episode. Stay nerdy. Einstein said nothing can go faster than light. Star Trek said, grand, we'll just leave space-time entirely then. Let's talk about subspace. These are 10 challenges to building a warp drive, and this is number 2, Star Trek and subspace. Now, in Star Trek, warp drive doesn't actually move you through normal space faster than light. It accesses an alternate dimension called subspace, where the rules are different. Now, the ship creates a warp field that shifts it partially into subspace, and in this state, the speed of light limit doesn't apply the same way. So you can travel at warp factor speeds, which are multiples of light speed. Now, warp 1 would be light speed, and warp 9 would be about like 1,500 times light speed. The Enterprise crosses the galaxy in months instead of millennia. Now, it's genuinely clever science fiction. Come on, we all love it. By inventing subspace, Star Trek's writers sidestepped Einstein's equations entirely. You're not breaking the rules of relativity because you're accessing a different layer of reality where those rules work differently. The problem here is that subspace doesn't exist. There's no evidence for alternate spatial dimensions that we could access for the purpose of travel. Now, string theory, sure, it does suggest that there are extra dimensions and they might exist out there, but they would be curled up at the Planck scale. That's like 10 to the minus 35 meters. Like, it's so small I can't even express it to you properly. Not traversable alternate realities that you could shift a spaceship into. So subspace is pure fiction, just a narrative device in order to make interstellar stories possible. But in 1994, a physicist watching Star Trek had an idea. But that's for the next episode. Stay nerdy. Most of us watch Star Trek and think, nice idea. Miguel Alcubierre watched it and thought, I'll just solve Einstein's equations and see what happens. These are 10 challenges to building a warp drive, and this is number 3, the Alcubierre metric. Alcubierre was a PhD student studying Einstein's general relativity. Now, he knew that while you can't move through space faster than light, space itself can expand or contract at any rate. Relativity doesn't place an upper limit on the rate at which space itself can expand, only on the speed of motion through space. During cosmic inflation, space expanded faster than light. Even now, distant galaxies recede from us faster than light because the space between us is stretching. So, Alcubierre asked, what if you compressed space in front of a ship and expanded it behind? And that's the key idea of the Alcubierre metric, space-time distortion rather than local motion. The ship wouldn't move through space faster than light. It would sit inside a bubble of flat space-time, stationary relative to its immediate surroundings. But the bubble itself would move by manipulating space-time around it. Now, he worked through Einstein's field equations looking for solutions that would create this geometry. He derived a metric that is consistent with the field equations, so it's mathematically valid. But it's a physically exotic solution. Now, you could mathematically construct a region of contracted spacetime in front, expanded spacetime behind, and flat spacetime inside where the ship sits. The bubble moves through space by surfing this geometry. He published the paper, I think it's called The Warp Drive Hyper-Fast Travel Within General Relativity. And physicists did genuinely get excited at the time, because Alcubierre had found a valid solution to Einstein's equations. Then, they calculated how much energy you'd need. But that's for the next episode. Stay nerdy. How much energy would a warp drive need? Let's just say, if you've got a spare Jupiter lying around, it could be a start. These are 10 challenges to building a warp drive, and this is number 4, the energy problem. Now, to compress space-time in front of your ship and then expand it behind it, you need enormous amounts of energy. Alcubierre's original 1994 calculation found that for about a 100-meter bubble, the energy requirement was on the order of the total mass energy of the universe. But that was just an estimate. Using some more realistic parameters, later estimates found that for a bubble around a ship the size of the Enterprise, which would be about 300-meter long bubble, you would need energy equivalent somewhere between Jupiter's mass and several times the Sun's mass. Still a lot. Jupiter's mass is about 2 by 10 to the 27 kilograms. That's 2 octillion kilograms. More mass than all the planets in the solar system combined. And you would need to convert that entire mass into pure energy using E equals mc squared, which would give you roughly 10 to the 44 joules. Now, to put that into perspective, the Sun outputs about 10 to the 26 joules per second. Jupiter's mass energy is equivalent to the Sun's entire output for 3 billion years. The total energy output of our entire civilization in all of human history is only about 10 to the 21 joules. So we'd need to collect our civilization's energy production for 10 billion times the age of the universe to match Jupiter's mass energy. That's just the energy, it's so much. I'm really struggling to give you a good idea of the quantities here, guys. But we're not going to worry about this too much, because when we're talking about amounts of energy, it's one thing, because it's just the energy requirement of what you need. The thing is, you also need the energy to be in a very specific form. But we'll get to that. The energy scale alone makes warp drive impossible with anything resembling current or foreseeable technology. Because we're not talking here about advanced engineering. We're talking about energy requirements that exceed what entire solar systems can produce. But in 2012, NASA announced that they'd figured out how to reduce it. And that's for the next episode. Stay nerdy. A NASA scientist once looked at the maths for warp drive and thought the trick might be to just change the geometry, change the shape, change the universe. These are the 10 challenges to building a warp drive, and this is number 5, NASA's geometry trick. Harold Sonny White of NASA's EagleWorks lab presented a modification of the Alcubierre metric at the 2012 100-Year Starship Symposium. Now, he didn't claim to have cracked warp drive outright, but he did propose that altering the bubble's geometry could drastically reduce the energy needs. The stress energy tensor depends strongly on the curvature distribution. So geometry changes the required energy density. Basically, the shape of the warp bubble affects how much energy you need. So Alcubierre had assumed a spherical bubble in his original paper, and White asked, well, what if you make it toroidal instead, which is kind of like a donut rather than a ball? By changing the geometry, making the bubble thicker in some places and thinner in others, you could distribute the space-time curvature more efficiently. So for a 10-meter bubble, you would go from Jupiter's mass down to Voyager's mass. Not that Voyager, that Voyager. That's about 700 kilograms. Now, NASA announced the results. Headlines everywhere. NASA was developing a warp drive. And for about 48 hours, everyone was really excited. And unfortunately, people do still bring this up whenever I talk about energy requirements. The thing is, pretty quickly, people checked the maths. The problem was that White had made some really optimistic assumptions. Basically, he oversimplified. When you properly account for maintaining the bubble's stability and achieving the necessary curvature, the energy savings disappear. The geometry helps, but it's not nearly enough. You still need astronomical energy. You're just arranging it differently. Now, another thing is that White's credibility also took a bit of a hit because around this same time, he'd been promoting the EM drive, which was supposed to be a device that supposedly produced thrust without propellant, violating conservation of momentum. Now, it didn't work. The results turned out to be just a measurement error, but ultimately NASA removed the EagleWorks warp pages and papers from its website back in 2019, although you can still get archived copies from the Wayback Machine if you're interested. So we still need huge amounts of energy for warp. But even if you could get enough energy, you can't get the right type of energy. But that's for the next episode. Stay nerdy. To build a warp drive, you'd need negative mass energy, basically stuff that does the exact opposite of everything we've ever observed. These are the 10 challenges to building a warp drive, and this is number 6, exotic matter and the Casimir effect. Normal energy curves space-time inward. It creates gravity. It pulls things together. That's how stars, planets, and galaxies form. But to make a warp bubble work, you need to expand space behind your ship. To do that, you need energy that curves space-time the opposite way. Matter that pushes instead of pulls. You'd need negative mass. Well, you'd need something that behaves as if it had negative mass, because negative mass would behave bizarrely. So does negative mass, or can negative mass even exist? Well, not as far as we know, but quantum mechanics does allow for negative energy densities, which is not really the same thing, and it only happens under very specific conditions. It's called the Casimir effect. You take 2 uncharged metal plates, you place them nanometers apart in a vacuum, and quantum fluctuations create a measurable attractive force between them. The energy density between the plates is slightly negative compared to the surrounding vacuum space. So can we use the Casimir effect to power a warp drive? No. The scale problem, it's freaking absurd. The Casimir effect produces tiny amounts of negative energy, and we're talking about forces measured in piconewtons, trillionths of a newton, between plates that are separated by nanometers. Warp drive needs negative mass equivalent to Jupiter. That's like 2 by 10 to the 27 kilograms. It's like something octillion kilograms. 2 octillion kilograms? Anyway, the difference between what the Casimir effect gives us and what we need is about 30 orders of magnitude. That's like a 1 followed by 30 zeros. The Casimir effect, it's completely useless for warp drive. Now, I hear you. You can't say what the future will hold. Well, what if someone did solve the problem? Well, sure. Say you find the energy, you figure out the exotic matter, you build a bubble. Amazing. You still can't get away from gravity. But that's for the next episode. Stay nerdy. Warp drive sounds great until you realize gravity's already warping space for you and it doesn't like competition. These are the 10 challenges to building a warp drive, and this is number 7, the gravity problem. Now, a warp bubble requires extreme space-time curvature. You're bending space so severely that it contracts ahead of you and expands behind. Near massive objects like planets or stars, space-time is already curved by their gravity. Each object creates its own gravitational field, its own space-time geometry. The Alcubierre solution assumes asymptotically flat space-time. So in curved or strong gravity regions, the geometry gets unstable. There's no stable analytical solution that combines Alcubierre type geometry with realistic planetary gravity. Try to generate a warp bubble in a region where space is already significantly curved and the two effects interfere. Your bubble's geometry interacts with the planet's gravity and things will get messy. The bubble would destabilize, collapse asymmetrically, or it could just create uncontrolled gravitational effects. Think of trying to create a whirlpool in water that's like already turbulent. The existing currents interfere with your whirlpool. This means that you can only safely engage warp drive in deep interstellar space, flat, empty space-time, far, far from gravitational sources. So you'd need some conventional engines to leave Earth's orbit, travel through the solar system, get well clear of the sun's gravity, light hours or even light days out, and then only then could you engage warp. Warp drive only works for the boring middle section of interstellar journeys, which sounds fine. You know, it's empty space between solar systems, nothing's happening anyway. But you still need full spacecraft capabilities for everything interesting: orbiting planets, landing, exploring solar systems, docking at stations. So what is warp saving you really? Because if you have to travel at impulse, it'll still take you years just to get to a safe distance before you could use warp drive. Then again, the distance requirements the gravity forces on you actually kind of helps you with the radiation problem. But that's for the next episode. Stay nerdy. Imagine a spaceship that destroys every planet it visits just by arriving. These are the 10 challenges to building a warp drive, and this is number 8, the radiation problem. Imagine the Enterprise drops out of warp near Earth. Before anyone knows that they've arrived, all life on the planet dies. You see, space isn't empty. There's roughly 1 hydrogen atom per cubic centimeter in interstellar space, plus photons from stars, cosmic rays, dust particles. The ship is moving through all of this matter, and the warp front interacts with surrounding fields and particles. So when you're moving at effective faster than light speeds, you're constantly colliding with this material. Here's what happens. As particles approach your warp bubble, they get blue shifted. So their energy increases dramatically. It's kind of the Doppler effect taken to an extreme. Low energy radio photons could become optical photons. Optical photons become X-rays. X-rays become gamma rays. The faster you go and the longer you travel for, the more high energy radiation that will accumulate on the leading edge of your warp bubble. The warped spacetime at the boundary traps it there. When you then disengage your warp drive, all of that trapped radiation has to go somewhere, and it will explode forward in a directed cone. The calculations suggest that this would be comparable to a gamma ray burst, one of the most energetic events in the known universe. Your arrival sterilizes anything in front of your ship. Atmosphere is stripped away, surfaces irradiated, all biological matter destroyed. And it happens at light speed, so like there's no warning. We come in peace! Oops! Now, there's no obvious way to prevent the buildup or to safely discharge it. It's a fundamental consequence of moving through a medium at superluminal speeds. And that's assuming you can even get where you're actually trying to go. But that's for the next episode. Stay nerdy. Space navigation looks easy in sci-fi. You plot a course, you engage your warp, and you hope you don't reappear inside a planet. These are the 10 challenges to building a warp drive, and this is number 9, the navigation problem. Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galaxy at around 200 kilometers per second. The galaxy itself is moving relative to other galaxies at hundreds of kilometers per second. There are no fixed reference points in space. Everything is in motion relative to everything else. Navigation across interstellar distances is a genuine unsolved challenge even for sublight probes. To plot a safe course at warp speed, you'd need to know the exact position and trajectory of every single object along your path. Every asteroid, every planet, every rogue comet, every dense gas cloud, everything. Because if you drop out of warp inside something solid, well, that's the end of your freaking journey, isn't it? The galaxy contains hundreds of billions of stars, trillions of planets and asteroids, countless comets. Interstellar space isn't empty. And the thing is, most of this stuff, it's dark. You can't see it from a distance. You only detect it when you're relatively close to it. So how do you map a route? The only way you would be able to travel is if at first you went at a slower speed, observed everything, tracked all the orbital mechanics and made a map. Then you could use warp drive safely. There's actually a really big problem with this, because by the time you've mapped the route, everything's shifted. Because planets move out of their orbits, asteroids drift. Your map is going to be out of date. So the navigation data needs to be constantly updated. You need the map to use warp safely, but you need warp to be able to make the map quickly enough to make the map valid before everything moves. Yeah. Isaac Asimov actually addresses this brilliantly in his Foundation series. His ships use jump drives, but they still need pilots who can calculate trajectories, accounting for all gravitational fields along the path. And it's presented as a phenomenally difficult and dangerous thing to do. Star Trek just ignores the problem completely, which, we're fine with. Come on. Now, in this series so far, we've covered energy, exotic matter, gravity, radiation, navigation. These are the problems that everyone tends to talk about, and they make it sound like warp drive is just an engineering challenge. That maybe one day, if we solve all of these problems, we'll manage it. But there's something much bigger here, something that breaks even the maths. But that's for the next episode. Stay nerdy. Does the math really say that warp drive could work? These are the 10 challenges to building a warp drive, and this is number 10, energy conditions. Now, we've covered 9 problems already, practical ones. Energy levels, exotic matter, radiation, gravity, navigation. These make warp drive sound like an engineering challenge. Fix enough problems and maybe we'll crack it. But that's not what the physics says. The Alcubierre solution is a legitimate mathematical solution of Einstein's field equations, but not one that fits physically reasonable energy conditions. You see, Alcubierre's equations violate fundamental rules that keep the universe working properly. And these are called the weak, the dominant, and the null energy conditions. These are the basic constraints that ensure that energy behaves normally in general relativity. Specifically, the null energy condition says energy density can't be negative along light-like directions. Now, you might be asking why? Well, it's because negative energy creates universe-breaking physics. It creates causality violations and time travel paradoxes. You see, every known form of matter mostly satisfies these rules. Yes, quantum effects can bend them locally, but they can never do it enough to do what warp drive needs. The Alcubierre metric violates these rules. The geometry that creates the warp effect requires violating the energy conditions not just once, but throughout the bubble. But between 2021 and 2022, a series of papers found ways around some of the energy requirements. But all of these papers, just like Alcubierre's original work, only look at one type of observer, one reference frame. But energy conditions have to hold for all observers in space-time, for all reference frames. When you check them all, the violations reappear, and this is not fixable. The space-time geometry that makes warp drive work is the same geometry that violates the energy conditions. Fixing one breaks the other. So even if you solved the energy level, exotic matter, radiation, gravity, navigation, you'd still be trying to create something that breaks fundamental physics. Star Trek's warp drive is fantastic fiction, but we can't have it. The stars are very far away, and they're staying that way.
Scotty, I can't change the laws of physics.
Thanks for following this series. If you want to dig deeper into those 2021 papers and why they failed, come and join the Nerd Club on Patreon. And I'll be back soon with a new series. Stay nerdy. Ooh, let me know if there's a series you want me to do. Bye.